All right, let's talk about something that sounds, well, a little crazy. We're going to dive into this fascinating paradox where we can actually make computers, these perfect machines of logic, run way, way faster by injecting just a little bit of chaos. I know, it seems totally backward, right? Computers are all about being predictable. You put in A, you get out B. Every single time. So why on earth would we ever want to throw something as unpredictable as a coin flip into that perfect system? Well, it all comes down to one thing: scale. 4.5 billion. That's a huge number. And that's roughly how many pages are on the web right now. And when you're dealing with a scale that massive, our perfect, logical, step-by-step methods, well, they start to fall apart. So what happens when you have that much data? Well, a perfectly precise solution, one that checks every single possibility, it just hits a wall. With billions of data points, the whole process becomes so slow, it's basically impossible. Think of it like a complete computational traffic jam. Just think about a service you use every day, like Google. A massive part of its job is to find and filter out web pages that are duplicates or super similar. Now imagine if it had to compare every new page to all 4.5 billion pages that already exist, one by one. The entire internet would just grind to a halt. And to give you a sense of just how bad it is, checking just 1 million documents, which is a tiny, tiny fraction of the web, would take a normal computer about 5 days. Now, try scaling that up to billions of pages. You're not talking days or weeks, you're talking centuries. It's not going to happen. So this is what that perfect but painfully slow method actually looks like. It's what we call a brute force approach. For something like an image search, it literally means comparing your picture to every single other picture in the database. It's guaranteed to find the perfect match, sure, but the cost? Time. Way, way more time than we have. So we've got to get smarter. And this is where the big twist comes in. The smarter way is to actually embrace a little bit of randomness. We're talking about algorithms that literally make decisions based on chance, the digital version of a coin flip. So what exactly is a randomized algorithm? It's pretty simple, actually. It's just a set of computer instructions that, at some key moment, uses a random number to decide what to do next. The key thing to get here is that the data it's looking at isn't random. The randomness is baked right into the algorithm's own logic. And this slide really shows you the difference in a nutshell. On the left, you've got your traditional algorithm. It's deterministic. You give it an input, you get the same output in the same amount of time. Every time. But look at the right. That randomized one, it introduces chance. Now, with the same input, the output, and even how long it takes to get there, can change. And that unpredictability, that's its superpower. Okay, so I know what you might be thinking. This just sounds like chaos, right? But it's not. It's a very, very calculated gamble. We're strategically giving up a tiny bit of certainty to get a massive boost in speed. And that gamble really comes down to one big question. What are you willing to risk? Would you rather bet on how long it takes to finish, or bet on whether the answer you get is absolutely 100% perfect? And that choice leads us to these 3 types of algorithms. First, you've got your standard deterministic one. No gambling there. Always correct, always takes the same amount of time. Then you've got what's called a Las Vegas algorithm. It always gets the right answer, but you're betting on how long it'll take. And finally, there's the Monte Carlo algorithm. It always finishes fast, but you're betting on the answer being correct. Let's make this super simple. Imagine you're looking for a 1 in a huge pile of zeros and ones. The Las Vegas way is to just keep picking random spots until you find a 1. You might get it on the first try, or it might take you 20 tries, but you will find it eventually. The Monte Carlo way says, nope, I'm only going to try 100 times. It's always super fast, but if it gets unlucky and only picks zeros, it'll just give up and wrongly say it failed. All right, so this all might sound a little abstract, but I promise you, this isn't just theory. This gamble is happening all around you, inside the tech you're probably using right now. A perfect example is randomized quicksort. This thing is an absolute workhorse for sorting data in pretty much countless applications. It's a Las Vegas algorithm, which means, remember, it always gets the sort right. By just randomly picking a starting point, it dodges the traps that can totally bog down its non-random cousin. So just how safe is this bet? Well, get this. A study by Microsoft found that for a large set of data, it is literally more likely for your computer to crash than for randomized quicksort to have a slow run. Let that sink in for a second. Your actual computer is more likely to physically break than this randomized algorithm is to have a bad day. That's how incredibly reliable this gamble really is. And this isn't some niche thing. It is everywhere, from analyzing huge streams of data that are too big to even save, to those similarity searches for music and images we talked about, to sniffing out copied content all over the web, and even powering some of the core models in machine learning. It's the secret ingredient that makes our modern, data-heavy world actually work. Which kind of brings us back to where we started, but with a new perspective. In a world that's practically drowning in data, maybe our whole idea of a perfect algorithm needs an update. The question we have to ask isn't just, is it 100% correct, but is it useful? Because let's be honest, an answer that's 99.9% right and shows up today is a whole lot better than a perfect answer that shows up next year, or maybe never.